practical application of a neural net model that we implemented in our nuclear fuel fabrication facility in Columbia, South Carolina for Westinghouse. And I'll start off with really showing you what the problem statement was and what the final conclusion was, but I really want to spend more time showing you really the details of what it took to build that model and implement it successfully, and a lot of the lessons learned and pitfalls that you may encounter along the way. So I want it to be that practical demonstration. So the work I'm going to present today is a result of a group of data scientists, data analysts, and engineers at Westinghouse that form part of our Westinghouse AI Center of Excellence. So I wanted to share that this is a successful product that has come out of this house, both internally and for our customers as well. So to get right into the example I wanted to share with you today, this has to do with creating sintered fuel pellets. Right? So the diagram on the screen is just a simple example, a part of the manufacturing process for fuel pellets. It really consists of taking uranium dioxide powder, compressing that in a press into cylindrical pellets, and then taking those cylindrical pellets through a furnace to sinter them into a ceramic, which forms the final pellet, which you can see over here on the right-hand side. So these are the final pellets over here. And there's a couple key characteristics that we need to satisfy when we're making these fuel pellets. And our application of a neural network model, as you'll see in a moment, focuses on being able to obtain those target results in these pellets. I'll also mention that for the most part, there are a combination of two powders that come together to create the pellet. The uranium dioxide, as well as U3O8, which is used as an adjustment for the final theoretical density, or the final density we get out of the pellets. And this is important. We call this add back. And so this is a certain portion of the powder is U3O8. And given that, we found over many decades of manufacturing nuclear fuel that the key output of our process is pellet density. We have to hit a very specific target pellet density for our customer. We've also learned that that density, the output of these centered pellets, is a function of many, many manufacturing and chemical process variables. So quite a few characteristics of that powder, as well as the manufacturing process of pressing those pellets and sintering them in the oven, all affect the density, and there's quite many sources of variation. We've also learned that the key element to adjusting the final density of the pellets is by adjusting the percentage of the U3O8 add back that we add to our powder. And how the manufacturing process has worked up to about almost 3 years ago is that for any given lot of pellets that an operator wanted to produce, when they begin to produce pellets, they will not know what the final density of that process will be. Because there is so much variation, they did not have the ability to really know what the final density was going to be before they started manufacturing pellets. So to get around that, they had an entire manufacturing process step that runs what we would call a trial run. They actually set the add back to a specific value, a nominal value, and generate a number of pellets in a trial run, and then take the finished pellets after sintering, which could be many hours of processing to get to that point, send them to our internal laboratory to measure the density on those pellets to find out what the end result was for that lot. Knowing what the final result was, they then made a human judgment on how to change the add back setting, how to turn the knob to get the final results that they wanted. So, and the bad part of that is not only did it take time to do that test run, but all of the pellets created in that test run had to be scrapped after they tested them. So it was a destructive test. So every single lot of pellets was causing scrap and cost of poor quality. So as well as, delays in time. So what was the solution? We basically built a machine learned model to replace that operator expensive trial and error process altogether, as well as their human judgment from experience on how to adjust the add back, to literally eliminate that process step. So the goal was train a neural net to predict ahead of time what the final density would be and adjust the add back accordingly so that the end result would be that we get the right density without creating any scrap. And so we did this by training a neural net with 5 years worth of manufacturing data that we had stored from the process. It predicts that manufacturing process and generates a recommendation to the operator of what add back they should use, where they should run the process at. And ultimately, this was very successful. After implementing it, we indeed eliminated the need to scrap those test pellets from every lot. That saves a significant amount of money every year. We were able to replace that human-based adjustment of add back that requires experience and many years of experience to figure out how to adjust that by their own understanding. We eliminated hours of hold time, and not only that, but this particular machine learned model, because it's recommending how the process is operated, and the operator then runs the process that way, and we get the results from it every single day for every lot. The data from those results goes back into the data set that the model learns from, and it continuously learns from us applying its own recommendations. So the outcome of its recommendations get funneled back into an automatic training and update every day for that model. Which is a really nice feedback cycle there. We implemented it about 2.5 years ago, and it's been in continuous operation ever since, and has performed very nicely. We've had a couple of process upsets that I'll discuss in a moment that weren't actually due to this model. All right, so here's where I really want to share some interesting information. And so I want to say, around the context of building that model and deploying it, what were some of the key technical aspects and challenges and lessons that we learned in doing so? So I'm going to break this down into some categories here. And the first one, and a lot of these lessons can apply to anything, any application that you want to deploy a neural net model or any other form of machine learning and AI. And the fundamental one is data, right? These are data-driven models. You have to have useful data. So one of the things that we learned was we started with what data was easily accessible to us, so that we didn't have to generate any new data. We didn't have to add any additional sensors to our manufacturing process. We looked at our manufacturing databases to see what was already available. Furthermore, you need to make sure that you partner with the data owners to truly understand what that data is. What does it mean? What are the underlying assumptions behind the, say, maybe columns of data that you could get from a spreadsheet, for instance? And from that, also, you need to consider that you may want to engineer features, choose features that have higher levels of information in them than others. So, for instance, if you're doing regression, continuous variables statistically contain more information than attribute variables. And you can quite often produce more capable models if you can get your data in a continuous variable form. We typically do exploratory data engineering analysis from that. So once we have obtained our data, this is the process of performing basic analytics, statistical inference, visualization of the data. And what you really want to do at this point is validate that what you're seeing, the subject matter experts or process experts agree with you on it. And quite often, here is where we'll find data quality issues or misunderstandings of what the data really means or inconsistencies in the data over time. And, a lesson here is really be prepared for quite a few data quality issues. You will find all kinds of things that you'll have to address and sort out before you can get to a quality, application of a predictive model. We've experienced in a number of our projects, and I think, worldwide, you'll find statistics like this, is that about 80% of the work in implementing a machine learned model or a neural net is really getting the data ready to be useful. That's not necessarily the fun part, but this is the hard part, and you should not underestimate how much that takes. In this particular application for the fuel, we ended up with about 100 features or 100 inputs into our neural net. These features were chemical characteristics of the powder, as well as process settings of the manufacturing upstream from where we pressed the pellets. We added an additional 5 inputs that are only known at the time of manufacturing by the operator. So the operator themselves provides 5 additional inputs, settings based on how they're currently running the operation, to the model as well. And then the key output of our trained model was the center density of the pellets. Getting into a little bit more detail, if you're going to try to create a model of something, you first have to be able to conclude that being able to make a prediction could be valuable or useful to you. Because that will lead to defining what the acceptance criteria, how well do you need to be able to predict something that's meaningful to predict? And so you have to ask yourself that question, can this prediction be useful to inform a decision that's being made, whether it's a manufacturing decision, a safety decision, an operating decision, a purchase decision, anything like that. And part of doing that is asking yourself the question, well, what happens if the prediction is right? And what happens if the prediction is wrong? Because all models are inadequate. They all have uncertainty, and there's going to be a certain percentage of the time that they get the answer wrong. And in this case, we had to ask ourselves these 2 questions, and getting the prediction right for fuel meant we got to save the amount of money and time for each process that scrapped a set of pellets for each lot, which was a few thousand pellets, say, for instance. So not a whole lot of money saved for each individual lot, and maybe about 4 to 6 hours of cycle time saved. But if we got the prediction wrong and we told the operator to run it with the wrong add back, the results came out bad, we might scrap an entire lot, which could be 100 times the amount that we saved. And so you have to take that into account. Model training, we basically, as I mentioned before, this particular model trains continuously. Every morning, it accumulates the previous day's manufacturing data, retrains itself based on both the historic and the recent data. We don't just create one model in this particular application. We actually automatically build about 15 different models automatically. These models compete with each other. So the best model capable of predicting the previous performance wins. Make sure you always compare any model you create to the grand mean of all your data, because if you can't beat the mean model, then you don't have a meaningful prediction. That's just a simple thing that sometimes people forget to check. But the types of models in this set of 15 have are the neural net is one of the primary ones. We also have support vector machine, gradient boosting machine, and k-nearest neighbors. And we have multiple variations, multiple hyperparameters on each of these models as part of that competition. Another subtle thing, a challenge that we ran into, was solving this specific problem. Right? One of the key questions that you have to ask yourself is, if you're building a data-driven model, how do you make the predictions from that model actionable? So let me explain what I mean by that. What did we really need to do? Our goal was really to recommend to the operator what input setting for add back they needed to use to get good results. But we were predicting density. That's what we were trying to predict. So there's 3 ways you could go about doing that. So this is what I call the methodology. We could literally predict use a forward model to predict the density, then solve mathematically for what add back we would have to get to move the density to our target for the customer. We could turn that problem around and we could conversely make a model that directly predicts what the add back would be when we set the target density that we want as an input. So this is an inverse model. We could just directly create an inverse neural net model. So, we could do a forward model and solve for the add back. We could do a direct inverse model, but here's the problem. We ran into a challenge with either of those two approaches. The relationship between add back and density that we have observed for many years is a causational relationship. We know by experimentation, by manufacturing, that if I move the amount of add back, I will adjust the percent density by a certain amount. And that relationship is actually kind of showed over here on the right-hand side. And you can see that relationship has a lot of variation in it as well due to other manufacturing variation that's present. But with a data-driven model, it's purely correlation-based. There is no guaranteed causation. So your model may not have the physical effect that you expect it to have. We knew that this was the physical effect that exists. This was the causation. And so what we found with the first two approaches is that while the direction of the effect was correct with the model, the actual amplitude of the effect was incorrect. So the sensitivity was not correct. And that's because, trained neural net models, their job is to match the training and validation data you give them in any way possible. And they will use the information from all of your feature inputs, not necessarily the ones you want it to use to define the relationship between a given input and an output. So what we ended up doing was creating what's called a physics-informed or physics-based inverse model. So we did a forward prediction of the density, and then we used a known physics model for the effect of add back on the density to then invert that back to get us the appropriate recommendation for add back on the input. So this is a case where in order to ensure the causation that we needed, we had to combine the neural net model with a physics-informed with a physics model as well. Once we've created the model, we have to actually validate that it can be trusted. And this is another key element, right? We want to take this model and we want to put it into production, and it's going to have real effects. It's going to potentially cause real defects or potentially save us from causing defects. And so we have to quantitatively assess how it might perform. How can we be confident that it's going to work? And one of the ways we do that is through simulation. We took the final model and historical data, and we did hypothetical what-if scenarios. We found all of the previous instances where we actually ran the process at the same setting as the model would have recommended it be run at had the model been present back at that time. And this distribution on the right-hand side represents the variation. The gray represents a wider variation of the existing manufacturing process without the model. And when the process historically followed what the model's recommendations would have been, you see the variation is less and on target. So this was a demonstration that had it been in place, it would have worked. And so from that, we were able to go into piloting. And so now let's put it actually on the manufacturing line and see what happens. And you do that in a small controlled approach. First, we connected it in parallel and allowed the operators to watch what its recommendations were, but not take those recommendations, just compare them to what they would have done and looking for anomalies, looking to see if it seemed to be consistent with what they would have done. After that, we run it in parallel for a little while, and we let the operators actually make changes to the process based on its recommendation. And then all along that time frame, we would also look for defects, anomalies, and we'd fix bugs in the software along the way. And then ultimately, after we ran it for a certain duration of time, we would reevaluate the statistics of the results to confirm that our initial estimates of how well it behaved was correct. And then for finally going into production, you really have to pay attention to the team and the users. For that, you have to have good, clear communication, especially early in life. Even when you implement into production, continuously monitor the performance of the model and the process so that you can prepare to respond to that when something may go awry. Ultimately, you need to continuously monitor the performance of your model. And furthermore, within the nuclear industry, because we are retraining models every day, we have an evolution of our model. We actually have to have reproducibility. So we need to go back to any point in time and be able to resurrect exactly what model was in place then and what was its predictions for anything. And so you have to have that reproducibility. So we actually archive all the models that ever get trained. One thing that we learned is that your users of the machine learning you have to consider their maturity in understanding machine learning or AI or neural nets themselves. And we found that immature users, people who are not used to using this technology, generally fall into two groups. Either they think of it as like a black box that they can't trust in any way. And so when anything happens, they blame the machine learning model instantly. It's kind of a reflex, a reaction. The other side of the coin is you get people that think that it's wonderful, it's magic, it can do everything because it's so amazing that they trust it too much. And because they trust it so much, they start ignoring other signals of things that could be going wrong. And either way, this results usually in the user blaming the model for any process upset that may be there. So once you deploy it, you have to provide support to the user. And you're going to find in operation that you may also have data quality issues that come back. You need to support the users in understanding of machine learning so that they understand why it's behaving the way it is when they have their own questions. And the other thing that we note is that this data, while we recorded this data from a manufacturing perspective, our manufacturing process wasn't actually dependent upon that recorded data. But now with the model in place, it is dependent upon the data. So you are changing the process or system to be dependent upon the data that your model is dependent upon. And that requires additional rigor and control of those upstream measurement systems and the process for collecting that data. Indeed, we had one issue where somebody improved the measurement system without realizing the dependency of the model on it. They actually increased the precision of a laboratory measurement, which sounds great, but it made the model effectively think that something went from a categorical type variable to a continuous variable, and it produced some improper predictions along the way. From that, we also added what we call input credibility checking. We also now monitor the inputs of the model to identify any abnormalities in those inputs and raise those along with live analytics to the operator. So they can make a decision to pause if something has gone awry upstream, because that's an indication if there's an anomaly in the inputs, there's an indication that you might not be able to trust the output of the model and you should take action. So with that, I will conclude. Really, my key points are there are really valuable and numerous applications of machine learning, as you've seen today from what everyone has been sharing with you. And don't underestimate the work really required to successfully implement them, especially in getting your data quality right and getting access to that data. Make sure that you can demonstrate the credibility of your model and its, and have confidence in its predictions, because you're really going to be dependent on its ability to predict what you need it to predict. You have to be able to translate that to a value demonstration and be prepared to support what you build. And it will be a perpetual support through the lifetime of the product. So with that, that concludes my presentation. Again, thank you very much.